So for today's lesson, we are going to build off of yesterday's conversation about logarithmic functions. Today we're going to talk specifically about graphing the logarithmic functions. Now in graphing logarithmic functions, we're also going to use what we talked about yesterday about how logarithms are very similar to exponents, and one relates directly to the other. One thing that you need to keep in mind is that exponents and logarithms, from a graphing standpoint, well, even from an equation standpoint, exponents and logarithms are inverses. Now, what this also means is that their graphs reflect over the line y equals x. Now, hopefully you'll remember that that's this diagonal line here. Okay, so let's go through and talk about this in a couple of key things, or excuse me, in a couple of key ways. First, I want to summarize a couple of details from the last lesson, which is the characteristics of exponent graphs. Now, this whole time we're going to be speaking specifically about the parent functions. And we're going to compare and contrast this to the characteristics of log graphs. Now, remember also logs is a way we often will refer to it, but log is short for logarithm. All right, so we're going to compare and contrast this to the log graphs. So, for example, point 1, we know that in exponent graphs in the parent function, you always have a point at 0, 1, and at 1, b. Remember, b is your base. Well, log graphs are the inverse of that, which means they reflect over this line y equals x. I don't know how many of you remember reflections from geometry, but when we do this, what we end up doing is reversing our x and y positions, which means the characteristic of the parent log graphs, instead of 0, 1, it is 1, 0. We are reversing the x and y. This also tells us that instead of 1, b, it is b, 1. And again, b is the base. You remember yesterday we said log base b, so whatever that small subscript number is. Another one we want to talk about is 2. The characteristic of the exponent is that there is an asymptote at y equals 0, or the x-axis. Well, again, this is going to flip. So for the log graphs, there is an asymptote at x equals 0, or the y-axis. Hopefully you're seeing these patterns here. And the last one, for number 3, again, we're talking about parent graphs, is the domain of the exponent graphs was x such that x was all real numbers, and the range was y such that y was all real numbers and y was greater than 0, because it had to be above that asymptote. Well, we're going to reverse this for the characteristic of log graphs. So now the domain is going to be such that x is in the set of all real numbers But x has to be greater than 0 because there's an asymptote at the y-axis. And the range is y, such that y is all real numbers. Again, everything reverses here. So I want you to keep these in mind as we go through a couple of examples. I'm going to go through one first, just so we have an example right here on this page, and then we'll move on. So here, if we take y equals 2 to the x power, well, then the inverse of this is your log function. Remember, 2 is your base, so y equals log base 2 of x. This is distinctly different than what we did yesterday. Yesterday we rewrote the exponent as the log function. Now we're actually representing the inverse of that function. So when we graph it here, right, we have our x and our y-axis. I'm just going to put a couple of markers here so we can see what we're doing. Keep in mind, for the y equals 2 to the x, we have a point at 0, 1, and at 1, 2. I'm going to put in here the line of reflection here at y equals x. So I'm going to first draw this one here. That's our y equals 2x. Now our logarithm, though, is the opposite. Remember, we're going to have a point at 1, 0, and then at 2, 1. And this time the asymptote goes along the y-axis, and we get the same look. And that's the difference between the exponent graph and the logarithmic graph. Okay, let's give some additional examples here. So what we're going to do now is I'm going to put a few out, just write some examples, and what I'd like you to try and do is to complete these first, and then once you have completed them, see if they are correct. So we're going to put out 4 or 5 examples initially. So number 1, y equals log base 3 of x. Number 2, y equals log base 5 of x plus 1. Number 3, y equals log base 3 in parentheses x plus 2. Number 4, y equals negative log base 3 x minus 2. And number 5, y equals 4 log base 3 of x plus 2 minus 3. And again, the concept here is I'd like you to pause this, try to graph each one of these, see how comfortable you feel, and then continue with this to see if you did it correctly. All right, so now I'm going to go ahead and walk through how to do each one of these, and hopefully you have had the chance to try this on your own and see if you've done this correctly. So the first thing you want to think about here is number 1 is what our first points are going to be, right? We have 1, 0 and b, 1. Our base is 3, So that b comma 1 is going to be 3 comma 1. That just helps you think about what our first points will be. So we go ahead and we draw the graph. Here there are two axes. Make a couple of marks. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And again, we're just kind of putting in some points so we can see what we're doing as we go along. And our first point is 1 comma 0. Our second point is 1, 2, 3 comma 1. There are no transformations happening here. So we know that there's an asymptote here along the axis here. And we can go ahead and draw in our graph. Okay, let's look at number 2 now. Number 2 is slightly different. I'm going to draw in that graph again here. Right? 1, 2, 3, 1, 2, 3, 4, 5, 6. 1, 2, 3, 1, 2, 3. Now we want to pause here and think about the fact that the parent function, remember here, is y equals log base 5, right, of x. So we know that we begin with 1 comma 0 and 5 comma 1. Once we have these, then we can look at our transformations that are occurring, and we're adding 1. So we're lifting everything by 1. So we have to remember two different things. First, when we lift everything by 1, that we are moving the y's. So our 1 comma 0 becomes 1 comma 1. And our 5 comma 1, 1, 2, 3, 4, 5 becomes 5 comma 2. So those are our 2 points. And our asymptote is still here, right along here, right, at x equals 0. That's still our asymptote. And now we can go ahead and draw this in. Okay. Number 3 is going to be a little bit different here. So let's go ahead and draw our graphs. We get x and y. Now remember, think about what your parent function is first. And then once we know our parent function, we can go from there. So we have our points of 1 comma 0 and our point 3 comma 1. But our transformation here is plus 2, which means we're going to move the whole graph to the left 2. So the first thing that I'm going to go ahead and do is show that we're moving that asymptote to the left 2. Because by doing that, that makes sure x now is negative 2 here, that we make sure we draw our curve correctly. Our 1 comma 0 moves to the left, so it becomes negative 1 comma 0, and our 3 comma 1 moves to the left also, 2, which becomes 1 comma 1. And now we can go ahead and draw that curve in. Okay, so this is basically the same thing that we've been doing the whole time. It's just a matter of doing it with logarithms. Okay, I'm going to draw this last 2 graphs in here, kind of to get them both drawn there. X and Y, and X and Y here. I'm just going to put a couple of marks here, and here we go. Put a couple of marks here. And the key thing to remember here now as we work through this is that we have a couple of different changes here. We start with our parent function of 1 comma 0 and 3 comma 1, but now we have to do 2 different things, right? We have to reflect it, and we have to bring it down. And when you do both of those, you should end up with 1 comma negative 2, right? Because we are going to go ahead and bring it down from 1 comma 0. And then also, the next one is going to be here, 1, 2, 3, comma, 1, 2, 3, and you're going to be down here. And now we will be able to go ahead and draw this in. If you'll notice here when we do this that we have not moved our asymptote, so it's simply going to go the other way, like this. Oops, I don't know why I deleted that, but that seemed to have gone away. And we still have our asymptote here. The last one here is a little bit more complicated than the other two, but I think we can do it. A couple things to think about here is we have a +2, which tells us our asymptote is going to move to the left. So I'm going to go ahead and draw in the new asymptote to get x equals -2. By drawing that in, I'm good. I know where the asymptote will be. We're also going to do our parent function here, right, which is 1, 0 and 3, 1. So we have 1, 0 and 3, 1. But now we have to do some stretches here. Now for the stretch, the first stretch, we can do it a couple of different ways. Let's do this. Let's move everything first to the left, 2. So we're going to go 1, 2. It's going to be our new one, and our new one will also be here. But now we're going to change our y value. I'm going to change our y value to account for that stretch. I just got to fix the laser pointer here. Now, when we multiply the first point by 0, that line just wants to be there, so I'm going to leave it there. It doesn't change anything, but when we multiply the second point by 0, by 4, it goes up. So let's put it up there. 1, 2, 3, 4. I guess it wanted to let us know which way it should go. But the final part here is we have to drop everything down by 3. So we end up, I'm going to change the color here just so it's easier to see. So we end up with that going a -1, -3, because we're dropping it by 3. And this point here drops also by 3. And then we are able to go ahead and draw in our new diagram or our new graph. So hopefully this gave you some insight into how to do these, and you will be able to complete the rest as you move forward. Have a great day.